my name is Sikka. I'm an engineer at Microsoft, and today I'll be talking about Microsoft EMET exploit mitigations. So an overview, EMET is what I'm going to be presenting. It's a tool that we release that is free and it protects enterprise computers from exploitation. And I'm also going to show how it does that with examples, and I'm going to show why it is very important for security to stay up to date with Windows versions. So the agenda is I'll be talking about what EMET is, explaining ROP exploits, giving a demo about how EMET stops ROP exploits, and explaining SCH overwrite exploits, and demoing how EMET stops SCH overwrite exploits. So I'll be talking about advanced defense techniques, not advanced exploit code and I'm not going to be giving you any zero-day vulnerabilities in any commercial software. Sorry. Okay, so first of all, I want to define what I'm going to be saying as a vulnerability and what's an exploit. A vulnerability is a weakness in a product that could allow compromise of integrity, availability, or confidentiality. And an exploit is basically data that's fed to the application to make it do things that is not intended by the developers of the application. So EMET stands for Enhanced Mitigation Experience Toolkit. It's free for customers, and what it does is it adds mitigations to applications running on operating systems as far back as Windows XP. And it does not require rebuilding and redeploying applications. That's a very big plus because, if it's like a hospital or something and the developers of the application have retired 2 years ago and you don't have the source code anymore, EMET will still protect you. However, it's not a substitute for upgrading Windows because newer versions of Windows have newer mitigations in them. And the main thing it does is it stops common shellcode behavior. And this could be useful even if you're being attacked by a zero-day vulnerability, because if the attacker is able to leverage the vulnerability but then not get shellcode execution, then there's no point of even having a zero-day for them. So it can protect against zero-day vulnerabilities. So EMET is ready for deployment in the enterprise, and it can be deployed via GPOs as well as System Center Configuration Manager. GPOs is group policy objects. And it logs data to the system event log, so then administrators of the organization can see, for example, when a computer had an attempt for a compromise, and when it was stopped. And another thing that it does is it protects Microsoft applications as well as third-party applications. So for example, we've tested it with versions of QuickTime and iTunes. And of course, we've also tested it with versions of Office and Internet Explorer and other Microsoft applications. And the way it works is it loads a DLL into the application's address space at runtime. So it dynamically protects the process, not at compile time or anything. So this past summer in Black Hat 2012, we released EMET 3.5 Tech Preview. And this is a screenshot. We have a lot of mitigations in there now. And some of the mitigations include DEP, which is data execution prevention. We implement the DEP mitigation by calling set process DEP policy. We mitigate heap sprays by pre-allocating locations common locations used by heap sprays. We also have mandatory ASLR, where we pre-reserve module base addresses where they prefer to be loaded, and that causes the modules to be loaded somewhere else because of a collision in the virtual address space. We have the null page mitigation, which pre-allocates the first memory page in a process, and that's more of defense in depth right now. We have EAF, which is export address table filtering. So we basically deny shellcode access to the export address tables of kernel 32 and NTDLL. Both of these modules, by the way, are very heavily abused by shellcode and attackers. We also have bottom-up randomization, which randomizes data structure bases. So for example, where different data structures are in the virtual memory address. So first of all, the heap spray, it's a technique that the attacker uses where they put multiple copies of their malicious code, like shellcode or something, into the process's address space, and they hope that a dereference or whatever vulnerability they're exploiting lands into one of the copies of their data that they put into the address space. And we have a mitigation for that. And the mitigation is that we pre-reserve memory at multiple virtual addresses where the attackers generally and commonly put their shellcode. And this reduces the chance that the attacker's allocation at the predefined address would succeed because it's already been reserved by EMET. So export address table attacks, in this, basically the EAT can be used to find the addresses of different functions in the virtual address space. So for example, you can find the addresses of like virtual protect and things like that, functions that are exported by common modules. And once the addresses of those functions are found, then shellcode can call those functions. So our mitigation for that is to set a hardware read breakpoint at the virtual address of the export address table. And this is both for the kernel 32 and the NTDLL modules. And when we do this, and the process tries to read that address, we hit the hardware read breakpoint, and then EMET performs a check at that point. And it checks that the current program counter, EIP register on x86, is pointing in a valid module and not on the heap or something, or on the stack, because executable code is in modules. So I'm going to be giving two demos today. The first one was the ROP demo that I wrote. ROP stands for Return-Oriented Programming, and it's based on ret to libc, and it's where an attacker writes an attacker-controlled call stack into the process's address space, and then they stack pivot from the real call stack that's being used by the process to their attacker-controlled call stack, and they do this by a stack pivot gadget. And the reason this is useful is because when returning, once they've already stack pivoted to the new stack, they use that stack. The stack contains information about where to return to. So they return to specially selected places, which I'll get to later. And these places are called ROP gadgets. So for example, it's a few assembly instructions followed by a ret instruction. And ROP gadgets can be chained together to achieve the attacker's intention without the attacker actually inserting code into the process. And so attackers, and ROP is a very commonly used technique because it bypasses DEP, which is data execution prevention, which is one of the mitigations that we introduced, because it technically does not execute read-only pages, but it's able to put the control data there. And also, oftentimes ROP is used to ROP to functions like virtual protect, which basically sets page permissions. So a ROP gadget is, like I said earlier, a few instructions followed by a ret instruction. So for example, as you can see, pop ECX ret or sub EAX4 ret. So basically, the attacker can chain these together and then ret from one gadget to another in order to achieve their intention. And oftentimes, the attacker has to be creative in finding ROP gadgets because they sometimes need to use instructions that are not normally emitted by the compiler, such as pop ESP, which is not a very common one. So they can do this by searching partway through multi-byte instructions. So if they decode the instruction differently, then they can get different behavior. So the stack pivot gadget, some examples of them are pop ESP, like I said earlier, or exchange EAX ESP. And in general, the stack pivot gadget that is to be used is very heavily dependent on the vulnerability because it depends on which register the attacker controls. So this is an illustration of a stack pivot. So as you can see here, right here, we have 1B9FA0 at the top of the regular call stack. That's the first step. Second step is that we execute pop ESP, and pop ESP will basically pop this value into the ESP register. Now, because the ESP register is the one that determines the top of the call stack, we have now 1B9FA0 is the same value that's in ESP now, and that points to the attacker-controlled call stack. So basically, the attacker just switch the call stack that the process is using, or that the thread is using, by calling pop ESP, and then they have a ret instruction. Ret would basically return to the address here at the top of the attacker-controlled call stack. So in the exploit that I'll show you, some of the things that I did were put certain addresses of certain functions onto the call stack that I introduced. So for example, you can see load library A, message box A, and then some parameters like user32.dll, and then some strings that I want to include. So EMET has ROP mitigations. So like I said, we released 3.5 tech preview this summer at Black Hat, and it was a result of the Blue Hat 2012 contest. And some of the things that mitigate ROP in 3.5 tech preview now include mandatory ASLR, which forces collisions by reserving virtual addresses at locations where modules say that they want to be loaded. And we also detour certain functions and perform checks at those functions. So we generally detour functions that are heavily abused, like load library A, virtual protect. And we also have memprotect mitigation, where we make sure that the attacker is not making stack pages executable. And virtual protect is detoured so that the attacker cannot enable execution permission on a page containing shellcode, for example. So some more ROP mitigations. These three mitigations were new to 3.5 tech preview. It's the caller mitigation, where we disassemble backwards from the return address at the top of the stack in the detoured function, and we make sure that the place where we return to is preceded by a call instruction, and that the call instruction's target was indeed this function where we detoured. And we do this to make sure that we don't ret into the detoured instruction, but into the detoured function, but rather we call into the detoured function. Another mitigation is simulation execution flow, simexec flow, where we make sure we don't ret from the detoured function into a place that's currently not executable. So for example, if the attacker was going to call virtual protect, and then the return address after virtual protect is done would be a page that is not executable right now. That means one of two things. Either they're calling virtual protect to make it executable, or it's a bug and it's going to crash because it's going to try to return to a page that is not executable. Either of those two cases is wrong. So we flag that and we mark that as an error. And another mitigation is the stack pivot check, where we check that the stack pointer must be between the stack base and the stack top for the process. Okay, so now I'll show you guys the demo. In a vulnerable program, and the vulnerability here is that we have a string copy, and we try to copy. Where's my mouse? Yeah, we try to copy 16 bytes into a 4-byte buffer, and that basically creates a stack-based buffer overflow. And before that, we just do other stuff, which is not as important, such as reading a file. But the file contains some data that the attacker will use later on. And here's where we call vulnerable, the vulnerable function above. Okay, so to prove that I'm not lying or anything, I'm not going to actually compile it in front of you. Okay, so it compiled. Now let's hope this exploit works, because they're always scared to work on stage. So this exploit works because they're always scared to work on stage. So as you can see in my code, I didn't have any reference to any message box functions. So you wouldn't expect any message boxes, but that's a hint. Okay, it worked. So I just called the message box function, and so basically what happened was that although the vulnerable code didn't have any references to the message box function, I still was able to call the message box function by wrapping around into the message box function. Now let's take a deeper look in a debugger to see how this works. as you can see on the top right, I have the assembly code that's going to be executed. So this part is not as important. Okay, so now this is the vulnerable function that we had earlier, and this was the string copy, which was unbounded, causing a stack-based buffer overflow. So we're going to ret, but I overwrote the return address to this. So if I show the top of the call stack, you can see that we're at the same value that I had here. This was what the attacker, the file that I used. This contains, oh sorry, this was the value that I overwrote the buffer with, or the EIP. So now, okay, now that was the address of the stack pivot gadget that I mentioned earlier. So now you can see the two instructions that I mentioned earlier right here. This is pop ESP and then ret. So pop ESP will, let me show you the call stack again. So as you can see here, this is 1B9FA0, which is this value here. So I had planted that value earlier to make sure that it would be the same address. So now we're going to pop ESP. I'm just going to execute this one assembly instruction. Okay, now let's dump the stack again. As we can see, the stack now points to the 1B9FA0, which was the value that I put in earlier. And so this means that now we are using the attacker-controlled call stack in the process rather than the original call stack. And from there, we just ret, and at the top of the attacker-controlled call stack is load library A, which is shown right here. So we just ret from there, and then the attacker can do whatever they want. So that's the dialog box. Okay, so now you saw the exploit working and how it works. Now let's see what happens when we enable EMET and we mitigate this. So like I said earlier, you don't have to recompile anything. So I'm not going to recompile. I recompiled the first time. I'm not going to recompile again. I'm just going to rerun the application after I enable the mitigation. So this is the stack pivot mitigation. I'm going to check this box. I'm not going to redeploy. I'm not going to recompile or anything. I'm just going to rerun the application. So you should see that it doesn't work this time. Nice. Okay. So EMET caught the stack pivot attempt, and it said that EMET detected stack pivot mitigation and will close the application. So now it would also log this to the system's event log. So any administrator in your organization can see that, okay, there was an attempt to stack pivot on one of the 100,000 computers in my organization. So let's take a closer look at that. So that's why this is useful for enterprises. And this is, okay, you can see that it just crashed. This is good because this means it didn't get exploited. It crashed instead. Okay, yeah. So now I'm going to talk about how to exploit structured exception handlers and how we mitigate that. So structured exception handlers, the support for that is a combination of Visual Studio Compiler as well as Windows. And what it does is it's a way to handle exceptions that occur at runtime. So as you can see here, we have the exception registration structure. And this is the call stack right here. So on the call stack, we have a chain of exception registration records. And each node in the chain has a previous attribute and a handler. And we have a chain that's followed all the way until we get to one node in the chain whose previous attribute contains -1, or FF, 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 FF. So what happens is that when an exception occurs, we're going to walk this structured exception handler chain, looking for which handler to call to handle this exception. Okay, but what happened? So this is an illustration of how this exploit works. So the first thing that happens is that there is a stack-based buffer overflow, for example, and we crush through our exception registration record, as you can see here, and we overwrite the previous attribute with EB069090, and then we overwrite the handler attribute with the address of what I'm calling an SCH overwrite gadget. So nothing is actually, all we've done is we've overwritten the record so far. We haven't actually hit the exception yet. So now we've hit the exception. So this could be like an issue in the program, or maybe the program had a null pointer dereference or something and an exception was thrown. But we still haven't executed our vulnerable code yet. So what's going to happen now is that an exception was triggered, and now we're in the exception handler. And as you can see, ESP points to the top of the stack as usual. ESP plus 4 is one D word under that, and ESP plus 8 is one D word under that on a 32-bit system. Okay, and so the first thing that happens is that we execute the handler, and we basically, go to the handler address and start executing there. But since we overwrote the handler address with the address of the SCH overwrite gadget, which is a pop ret, it's going to execute pop ret. But as you can see at the top, I have ESP points to the top of the stack, ESP plus 4 points one D word underneath that, and ESP plus 8 is one D word underneath that. So you would pop ESP plus 4, and then ret to ESP plus 8. And as you can see in the exception handler, ESP plus 8, which is this part here, always points to the first node in the chain, which we've overwritten with EB069090. So basically we're returning to the value stored here, which is this address. So now we start executing EB069090. EB069090 is the x86 instructions, and it's the machine code for jump 6 bytes, and then NOP, and then NOP. EB06 is jump 6 bytes. So what's going to happen is we're going to jump 6 bytes forward from where we are right now. And jumping 6 bytes forward, you would jump over the first 90 byte, jump over the second 90 byte, and then jump over the next 4 bytes, which is the SCH overwrite gadget address D word, and you will land in your shell code. So that's how you exploit a structured exception handler. And just so in WinDebug, before we have the stack-based buffer overflow, on top I've dumped what the exception chain looks like, and you can see that it's healthy and normal. You can see that it's except handler 4 is registered. After the stack-based buffer overflow, when I crush that record, it's pointing to an unrelated part, some unrelated code, which in this case is CRT waiting on module handle. This was some of the data that I overwrote with. So EMET also mitigates this with the CHOP protection, structured exception handler override protection. What it does time ago, instead EMET can be used to later on bring the support to Windows XP. So for example, if you're that hospital that it wants to protect your software, you would run EMET, and even Windows operating systems as far back as Windows XP would be protected by this. But like I said, newer versions of Windows have all this stuff built in. So for example, Windows Vista Service Pack 1 already had this built in. So now I'll show you the demo of the SDH override. Okay, so as you can see here, I have some small code. If you all can't see this, I can make it bigger. Okay. So hopefully all can see that. So this is another vulnerable code snippet where I have a vulnerability, and what's happening is that I'm reading input.bin here, and I don't check the size of the input.bin. I just automatically read the whole file. So if it's too long, we can overwrite stuff on the stack because I'm reading it into a variable that's on the stack, and so the attacker controls just the file. And so the actual vulnerability is that we don't restrict the size of the file that we read. And here is where we have just some exception that could occur during the program's execution. So again, to prove to you that I'm not lying or anything, I'll compile in front of you. Okay, it's compiled. Now I'll run it. Okay, cool, it worked. So in this case, what happened was that as you can see, there's no reference to message box function in the code, but we saw the message box coming up because that's what the shell called. So that proves that it's been exploited. Now, and we're going to start execute. Okay, this is the assembly code on the bottom left here. So look at this one. Okay, this is the function. Okay, so as you can see, this is a call instruction, and this is calling that location which I said earlier, which is CRT waiting on module whatever. So basically, we've overridden that pointer to the handler pointer, and now we're going to call that handler pointer that we overrode. So as you all remember, this was the pop ret SCH override gadget that I mentioned earlier, right here. So we're going to pop ret. Okay, now this is the EB069090 that I mentioned earlier. So this is basically the code that just jumps over the next 6 bytes. Okay, and now you can see this is where I call load library A right here, and then the message box A function. That's how I got so I basically wrote this shellcode here and some more above. I wrote this part of the shellcode to basically be executed when the handler is exploited. So if I hit F5, okay, there you go. So it just popped up again. Okay, so now let's enable EMET, and let's see what happens. So like I said earlier, this is the hospital application, and you don't have the source code, or the developers are retired or whatever, and you just can't change it or redeploy it. So you just use EMET, and you check this checkbox here for the SCH overwrite C-hop protection. And then now when somebody tries to attack it, I see I'm not going to recompile it, I'm just going to rerun it. Okay, cool, right here. EMET detected SCH OP mitigation, and we'll close the application. And it crashed, which is good, it didn't get exploited, it crashed instead. Okay, so as I've been saying throughout the presentation, newer Windows is safer. So for a progression that you can see of security mitigations that we've added to newer versions of Windows, we have DEP, which was introduced in Windows XP Service Pack 2, and attackers used ROP to get around DEP, and that's a sad face because that's bad. And then ASLR was introduced to break ROP, and that was added in Vista, and that's a happy face because that's good. And then after Windows XP, for applications running on operating systems past Windows XP, EMET can force ASLR on programs even if they were not compiled with dynamic base. So in general, as you can see, upgrading Windows is recommended to stay safe, but for the hospital situation where they can't upgrade Windows and they can't redeploy and reinstall everything because it's been already approved or whatever, they can at least use EMET to make it safer. So here's the effectiveness of EMET in a study of 100, as you can see on the bottom, on the first column, Windows XP Service Pack 3 had 181 successful exploits in our test. And all we did was enable EMET on Windows XP Service Pack 3, and it dropped drastically from 181 exploits that worked to 21 exploits that worked. But as you can see, upgrading Windows further reduces the number of vulnerabilities that were successful from 21 to 10. So the call to action here is to deploy EMET to protect enterprise computers from exploitation, because sometimes even although it's recommended to upgrade Windows, you can't. This would still protect your applications, and when possible, try to upgrade Windows to stay latest with the security mitigations that are built in. Here's the references. I have a lot of the links to things like where to download EMET for free, because it's a free tool. I have links to the Blue Hat contest and some papers that I referred to. And thank you.
Not really that easy to use. Iron was